Okay guys, in this video we're just going to look at a few worked through examples of how you might solve a quadratic equation when it's not as easy to do by graphing, and also using square roots isn't a possibility. And so the third way, and actually this is kind of our mainstay here in algebra, is to set everybody equal to 0 and factor it. And so what we're going to be doing is utilizing what we call the zero product property when we do this. And so the zero product property, let's lay this out here. We say if I'm going to put asterisk b equals 0. In other words, if a times b equals 0, we can say then either a equals 0 or b equals 0, or both equal 0. So in other words, essentially what we could do is we could rewrite these expressions as two things multiplying out to be 0, two or more things multiply out to be 0. Then we could take its constituent parts, each of those factors, and set them individually equal to 0 and solve it. So with respect to solving by factoring, I think the idea is that the first thing we want to do is make sure that we do indeed have a 0 on one side. And so that's what we're going to start with first here on number 24. Now I notice on 24, just to kind of talk you through this here, let me try the other side of my pen tool here, that I have an x squared and an x to the first. And so solving this using square roots isn't going to be a possibility. So if that's not a possibility, like we've mentioned here, what we're going to do is we're going to clear an entire side. So I'm going to subtract 6x and 7 from both sides of this. And what we get on the left then is just x squared minus the 6x's minus the 7 that I just subtracted. And on the right, we just get these to cancel. So the first step of this process is already done. We're already set into standard form and set equal to 0. The next thing we're going to do is factor this. So factoring wise, remember you always check for a greatest common factor amongst all your terms first. And I notice that these share no other common factors other than 1. So to move on, we'd say, well, then I notice it has 3 terms here and that its a value is 1. We can factor this as a product of two binomials, where what we're looking for is, if it factors, two numbers that multiply out to be -7 and then add up to be -6. So with respect to what these numbers are, I can kind of say, well, if they add up to be a -6, and it multiplies out to be a negative, they have opposite signs, and these numbers would have to be a -7 and then a positive 1. So our two factors become this x minus 7x plus 1, and this equals 0. So now that I've got this factored, here's what we're going to do. We're going to look at this as, this is like my a, and this is like my b with respect to our zero product property. And because a times b equals 0, then either, and I do like to draw these arrows here to show you work, we say either then x minus 7 equals 0 or x plus 1 equals 0. So to solve these, this is, hey you guys, this is a piece of cake. So I could add 7 to both sides here, I get x is 7, or I could subtract 1 from both sides here, and what I get is x equals 1. So my two solutions in this case are 7 and 1, and that's pretty nifty and easily done when you have this thing set equal to 0 and factor. So let's try again here. Looking at this one, dead giveaway that I have to use factoring is that I have an x squared and an x to the first. And so what I'm going to do again is, we're going to start by getting this set equal to 0. That's the whole premise, is that I can get it set equal to 0 first. But I would get this guy right here. Now in terms of factoring, again, remember what I've mentioned all the time. You always check for what first when you factor? Well, your GCF. So I notice here that both of these terms share a common factor of x. So if I take that x out in front, what would I have left over on the inside? Well, x squared divided by the x I took out in front would just be a single x. And then positive 4x divide out the x, we just get left with just plus 4 equals 0. So now, a lot of times I get people that get stuck at this point, and the reason why is because they don't see two binomials that multiply out to be 0. But I do want to point this out. We do have two factors in a product that are multiplying out to be 0. So either the first factor, which is x, either that equals 0, or the other factor here, x plus 4, equals 0, which in this case I'd actually have to go and finish solving this by subtracting 4 from both sides, but we would get x equals -4 here. Okay, and then looking at this last one, now this usually confuses people also, but because there are just many terms, what I want to point out is, hey, if you've got an x squared and an x to the first in the same equation, you're going to need to rely upon factoring. So what we're going to do is we're going to pick a side here, and we're going to clear the side completely. So I'm inclined to clear the right side for a couple of reasons. One big reason is this, because if I clear the left side, then what's going to happen is my a value, or my leading term, is going to have a negative on it, and that's just not helpful when you factor. And the other reason is, well, I guess just because of this x squared, I want to leave it where it's at. I want to leave it positive, so we're going to bring things over here to this side. So I'm going to subtract 12x and add 48 to both sides here. What ends up happening on the right, of course, is that we get 0 naturally. On the left side, we get 2x's squared. Now, -12 and -16 in terms of x's here is negative, that'd be 28x. and then we say plus 48. So again, as we do, we say, well, let's go factor this. Well, the first thing I notice is that there's a GCF here. And that's kind of nice because when you take out this GCF, your terms on the inside that get left over are going to be all naturally very much smaller most of the time. So if I factor out the 2 that they all have in common, we'll put 2 out in front. Let's see what we have left here. I'd have just an x squared. Half of negative 28 is negative 14 if I divide that by a positive 2. If I divide 48 by a positive 2, I get 24. And so the benefit to doing this then is that this just became a little bit easier to factor. That is to say that there is no longer a GCF and it's a trinomial 3-term thing with an a value of 1. So now all I really need to consider is, do there exist two numbers that multiply out to be a 24 that at the same time add up to be a negative 14? And so they both have to be the same sign since they multiply out to be a positive, but they have to add up to be a negative, meaning that both of these are going to have to be negative. And furthermore, we say, well, what multiplies out to be 24 that are both negative and add up to be a negative 14? I can think of negative 12 times negative 2. So this means that our factors then become x minus 12 and x minus 2. Now in this instance, this is a little bit different than the first two examples. This has 3 factors that are multiplying out to be 0. And so either x minus 12 equals 0, or x minus 2 equals 0, or one thing I want to point out here is this: it would be absurd to say that 2 equals 0 because 2 never equals 0. So what I want to say is, whenever you factor something, if one of your factors is just a number, then we don't set that number equal to 0, because what we're looking for is, what do the x values in our x expressions have to equal for those expressions to collapse to 0. So adding 12 to both sides of this one here, suppose we get x equals 12, and here if I added 2, I get x equals 2. So distinguishing between all of these, one thing that I want to do, and this is pretty powerful, but is to go back up my graphs with, or sorry, my work with some graphs. So what if I were to actually go and take these equations, these original equations that were set equal to 0, and go graph them? What would I expect to see on my graphs here? So what I did before I started this video was exactly that. You can see that x squared minus 6x minus 7 is my first graph here. When I hit graph, we should anticipate that we have zeros or x-intercepts at 1 and 7. So we look at this here, and sorry, negative 1 and 7. That would have been a close call there because we did subtract 1. Geez, Mr. A. So when we look at this here, we'd say at negative 1 on my x-axis, and if I count 1, 2, 3, 4, 5, 6, 7, those are the two x values for which our graph hits the x-axis. Now when I look at this next problem, we anticipated it hitting at 0 and 4. So let me take its equation here, and we'll get it typed in. As a matter of fact, it's already typed in. But remember, we're taking the equation that we'd set equal to 0 and putting that in. So we say x squared plus 4x. Let's take a look here. Looks like it crosses at negative 4 and at 0 on the x-axis, and we can clearly see that we get 0 and negative 4 here. And then for our last graph here, I'm going to go back to y equals. We'll turn off our second graph and we'll turn on our third graph here just to check it out really quickly. This is the equation I got when I set it equal to 0 first, so that's what we're graphing. And as I go graph this here, we're expecting it to hit at positive 2, which it does. You say, well, where's the right side of my equation? Well, it hits at 12 here. And so what I'm going to have to do is change my window so that my x max goes out a little further. Maybe we go out 15 on the right. But if you take a look at this here, we say it crosses at 2. And if this is 15 on the right, this is 14, 13, 12. So just keep in mind that when you're solving these things, these quadratic equations, what you're really doing is looking at the x-intercepts of your graph. Okay? Cheers.